right. So today we're going to start our first theoretical lectures, and we are going to start with the probability concept, but we are going to build some background in statistics. So let's start with a brief introduction. All right, so let's first start with probability. What probability does? Like probability, why do we need probability? Do you guys know why we say, like when I see a specific event, oh, the probability of this computer to break down in the next 20 years is like 20%. So probability is a measure that, or a tool that can measure uncertainty. So there's something uncertain that we don't know. So how to measure it? We use the term probability, or we use the probability to measure how certain a specific quantity is. And that applies for, I believe, everything in our life is uncertain. Living in this life is uncertain. Even in a structural engineering concept, so sometimes you misconceptualize all the background that you have in structural engineering. Oh, I have this beam in a bridge and it's gonna have a load of 100 tons. It's never gonna happen. There is no specific 100 tons that is gonna be a load on this beam. It's uncertain. The load is always uncertain. The strength of the beam is uncertain. All the conditions are uncertain. So right now I need you to shift the concept. Like, I know that what we are trying to solve actually in this class, in structural engineering, So in structural engineering, you were solving this problem. Like you have, for example, load B equal to 10 ton, and you find the bending moment and the shear force and the normal force. Right now, this whole concept is gonna collapse. There's no such a thing as a 10 ton on this beam. This is gonna be like the mean load on this beam is gonna be 10 ton, and the standard deviation of this load is like 2 ton. That's how we make the load uncertain on this beam, and that's actually how its real life is. Like when we calculated the life load on this system, we said, okay, this system is an educational center, and the life load is like 0.2 tons per meter squared. So that's our mean load, but the thing is, what's happening in real life? We're just like maybe, I don't know, 20 people, maybe another class is gonna be 50 people, another class is gonna be 30 people, so the load is fluctuating. So it has many values. So we need to take the mean and the standard deviation so that we can come up with a way to measure how certain is this load on this system, right? So how we can do this and how the codes find the value of the live loads, they collected a lot of data. They collected like, okay, this system can have this. Picking the extreme value is really bad because you are going to end up with having a very expensive system. And also picking the lower value is unsafe. So you need to come up with a value that is not extreme and it's not very low, and it's something that takes into account the uncertainty of the load. That's what we are trying to do. So let's say that we find out that this is our mean load and this is the standard deviation. The consequences is going to be that the reactions here are going to be deterministic or probabilistic. You'll end up with having a V that has mean and also standard deviation, and here mean and standard deviation. One of the homeworks that we're going to have later on in this class is going to be something like this. If this is just a deterministic load, it's going to be the most easiest problem in structural engineering. But since I give it to you as a mean and a standard deviation, solving this problem is maybe will take like 1 to 2 pages to solve. Okay, so that's what we are trying to do. So the introduction of this class is that everything is probabilistic, and probability is a mean or a tool that can measure the uncertainties in the structural parameters. Okay, so there's 2 different types of uncertainties. There's something called aleatory uncertainty. there's something that's called epistemic uncertainty. So what is the difference between the aleatory uncertainties and the epistemic uncertainties? So the thing is, there's some uncertainties that we cannot get rid of. Like, okay, you told me like, I don't know the load of this slab. So to measure the uncertainty of this slab, I have to collect a lot of data about the students that comes in and comes out so that I can come up with how uncertain is this load is. And the more data that I collect, the more I can capture this uncertainty, right? So that's what we call here epistemic uncertainties, uncertainties that you can get rid of if you collected more data. But there's something is called aleatory uncertainties that you will never get rid of. Like let's say that you are flipping a coin. When you flip a coin, you either get a head or tail, so the probability is 50-50. You cannot make this probability as 40-60. So it's always gonna be the way it is, and it's irreducible. You cannot reduce it. Same thing, rolling the dice. If you are rolling the dice, the probability is 1/6. You will get 1, 2, 3, 4, 5, 6. Everyone has a probability 1/6. You cannot reduce this unless if it's unfair rolling of the dice. If you try to make something to temper with the whole events that you are gonna get, so it's gonna be this rule is not gonna be applied. So it should be fair rolling of the dice or fair flipping of the coin. That's what we call aleatory uncertainty. You cannot reduce this uncertainties, but the epistemic you can reduce that. So what is examples of epistemic uncertainties? Do you guys can give me examples? Like collecting any types of data, like going in the lab, breaking a bunch of concrete blocks, or breaking steel coupons, or collecting wind speed data. All this, the more data that you collect, the more information that you have about the element that you are studying, and the more that you are reducing the uncertainties in your analysis. Okay, so the absolute reliability of the system, like you cannot be 100% reliable of your system. Like building this structure, you think you are safe, but with a specific percent, maybe 98%, maybe 95%, but you are not 100%. So 100% reliability in a structural engineering is not it's not attainable. You cannot attain this. So we always do our analysis with a specific probability. Okay, even the loads, if you dive deep into the ASCE 716s, the loads, there's, I believe, a commentary about how the uncertainties are captured. They will talk about are we, like we are at the 95% about like when we capture the uncertainties of the data, and they have the distribution. So basically, when we design, like let's say, we are gonna come later to this in details, but I'm gonna give you a little bit of an idea. So let's say this beam is gonna be exposed to a 10-ton, but the 10-ton is the mean and has a standard deviation. So when you capture the normal distribution, and we're gonna talk about the normal distribution of this, so the mean is gonna be like 10, right? And this load has a normal distribution that it can be lower than 10 or much higher than 10. We don't know, but this is the distribution of the load that this beam is gonna get. I want the resistance of the beam to be much bigger than this. So the resistance of the beam, or the resistance of this beam, it needs to be more than 10. But the thing is, how it's gonna be more than 10? I mean, like, I'm gonna design for this. No, we're not gonna design for this. We need our resistance to be something like this. Maybe here is 15. But here is the problem. Why? Yes, my mean here is 15, but this mean maybe you can have a resistance of the beam as low as maybe 12. And you end up, but the 12 is like at the 95% chance to happen. This is the 95% chance to happen. Maybe at the 2% chance to happen. So you might end up with an event. Then you have the resistance of the beam, 2% chance to have it at 12, and the load is at 98% chance to happen. And this is when the failure can happen. But what is the probability of this? Maybe 1%, 2%. Can you tolerate this in your analysis? Yes, I can tolerate this in my analysis. But what if I want reduce this probability to be 0.001%. So you have to increase the resistance and decrease the load. Or if the load is constant, you have to increase the resistance, so you lower what is gonna happen here. Okay, we're gonna talk more about these two curves in the future. All right, so let's go to the next. So how we can measure the probability. So there's something is called a statistical regularity. All right, so how we can capture these two curves? We need a lot of data so that we can know what is the resistance of the beam and what is the loads on the beam. So how we can do this? To know the resistance of the beam, the thing is you need to find the characteristic, the characteristic compressive strength of the beam. So let's say that we are gonna do an experiment in the lab and bring a lot of concrete blocks from the concrete that is going to be used to make this beam, and we are going to end up with 100 concrete blocks, and we're going to break all of them. So when you break all of them, so you're going to end up with having a lot of values, maybe the compressive strength, let's say 25, and some is lower than 25, and some that they are bigger than 25. So that's actually, how is this distribution of everything? Like if we collected the data about all the heights of us in the class. Some of us are gonna be 6'1", some of us are gonna be 5'5", 5'7", and we put them in a graph, it's gonna be something like this. Our ages is gonna be something like this. So that's actually most of the distributions is gonna be something like this. And we call this, yeah, that's what we call the probability density or the probability mass function, because it's discrete, like single points. And it can be probability density function if we fit them like something like this. Probability density function. And this, the value here is the mean. Later we're going to talk about the mean and the mode and the median, and we are going to have a lot of parameters, but that's what I want you to get in your head right now. All right, so let's talk about the basic concepts of probability, because that's very, very important to have in mind. So when I start to get to know the probability of a specific event to happen, the thing is you need to have an experiment, like rolling a dice or flipping a coin. We call all these experiments, or going to the lab and do an experiment on a concrete blocks and collect all the data of the failure of these blocks in the lab, or going collect wind speed data. So you need a specific experiment. So number one, we need experiment. Number two, you need sample space. So doing the experiment, you need sample space. Like you need rolling the dice. What is the sample space of the rolling the dice? You might get 1, 2, 3, 4, 5, 6. Flipping a coin, head and tail. That's all the sample space. And we give it the symbol omega. That's what we call the sample space. So, and there is events that can happen during this experiment. So number 3, it's called events. What is events? Events is like getting 1 and 2 from flipping a dice. We call this event. You can make up any events. Like you can say, I'm only interested in getting 1 from rolling a dice. I'm only interested of getting a hit or in flipping a coin. Or I'm only interested in events that has wind speed 160 miles per hour. So you can say, I'm only interested in events that are having wind speed that less than 30 miles per hour. That's still an event. So we call all these events. But the events doesn't have to be everything in the sample space. Maybe just one thing happened in the sample space. It's called event. And number 4, which is the last one, it's called a probability assignment. So what is the probability assignment? You specify a specific event, like rolling a dice and getting a 1. So you need to find what is the probability this event to happen in the entire sample space, which is 1/6. Flipping a coin, what is the probability of getting a hit? That's probability assignment, which is 1/2. So the probability of a specific event to happen it should be more than and less than. Definitely probability of event should be more than or equal to 0 or less than or equal to 1. There is no probability that can be more than 1 or less than 0. There is no probability that is negative. So that's something that we need to keep in mind. But this event needs to be as a part of the sample space. Like you cannot having an event of rolling a dice being a part of flipping a coin. So it needs to be part of the same sample space. So let's have a little bit of an example here. Okay, let's actually put it in the same thing. So let's say that we have an experiment of tossing a dice, and you are observing the number on the upward face of the dice. So that's the event. The event name is tossing dice. What is the sample space of tossing a dice? 1, 2, 3, 4, 5, 6. That every event that can happen from tossing a dice. What is events that I'm interested at? Maybe you are interested at event 1 where n equal to 1, or event 2 that the number upward need to be more than 3, or event 3 where the number is more than or equal to 3. That's all events that you might be interested in. So let's find the probability of each one of these events. Can you tell me what is the probability of event 1?
1/6.
1/6. The probability of event 2? Okay, it can be 1 or 2. So, oh, sorry, more than 3. So it's gonna be 4, 5, and 6, which is 3 numbers, so it's gonna be 3/6. How about this one? 3, 4, 5, 6. So it's gonna be 4/6. That's the probability assigned. Same thing if I said maybe it's gonna be the same thing. Tossing a dice, and my sample space that I'm looking at is odd or even. What is the probability of getting an odd number? 3/6. What is the probability of getting an even number? 3/6, right? So you can exchange the sample space that you're looking at or the events that you are interested in, okay? All right. So, let's talk about 2 events together, not only one event. Right now I'm interested in the probability of event 1 and the probability of event 2. What if I'm interested in 2 events that are happening together? And it's still events from rolling a dice. But before we do this, I believe you guys all have done maybe at some point in the classes that you have taken in the past. Like, let's say that this box has all the sample space that you have. Maybe all the sample space from rolling a dice, from flipping a coin, from collecting data in the lab, and you have an event A, an event B. You guys remember this? Something like this? Okay. So every event in this sample space, like let's say I have this events, every event is called outcome. And the sample space, as we said, is gonna be omega. And this is event A that might have some outcomes. And this is event B might have other outcomes. And event A and event B some have common outcomes together. Okay? So let's see an example of this. If you are rolling a dice, and let's say that we are interested in event A where when I roll a dice, I get 2 or 3. And there's event B where I get 3, 4, or 5. Okay? So if I try to do this in that way, all right. So I have event A, but by the way, they share something. 2 and 3, there's 3 here. So this is event A, and this is event B. So event A, let's write A and B, has 2 and shares 3 with event B, and B has 4 and 5. But rolling the dice have 1 and 6 as well, right? But 1 and 6 is events that I'm not interested in. I'm interested in event A and event B. But getting 1 and 6 is still and one of the outcomes from rolling the dice. Okay, so what I'm asking for here is what is A union B? What is the probability, or not the probability, the events that happens in A and B? That's all the number in A and B without like double counting. Okay, so A and B, like to get A and B, that means you can get 2, 3, 4, and 5. That's all the events that can happen in A and B. So 2, 3, 4, and 5. What is A intersection B? 3. It is 3, right? That's the only event that happened in A and B together. Okay? Do we get that? All right, so let's learn something else. It's called the complement of A. What is a complement? Complement, like, let's say that this is my sample space, and this is event A, and event A has 2 and 3. That's A. Anything that is not A is called the complement of A, which the entire sample space except event A, which has 1, 4, and 5. We call this A complement. So A complement, which is, I can write it 2 and 3. 2 and 3, this is A, but if I put bar on top of them, that means the complement of these events, which is gonna be 1, 4, 5, and 6. But tell me, if I trying to get the union of A and A complement A, what this is gonna give me? The entire sample space. Okay? What if I want to get the intersection of A? It's gonna be 0, the empty set. We call it phi. Okay? Say this is sample space. This we call phi is the null set or empty set. Alright, so let's.
I have a question.
Yeah.
So is A represent having 2 then 3? Does that?
Yeah, like all, like, okay, so the event can be, A is a set of events that can happen,
Okay.
that has multiple events. So sometimes you are interested in one number, and sometimes your set has many numbers. Sometimes you're interested in the wind speed that are less than 30, so anything that is less than 30 is entire your set. So it doesn't have to be one single number.
Okay. And why do you call the ones that off the circle as events? Are they space samples or are they?
They are space sample, but you can include them in one group, and we call this group the complement of A.
Okay. But
And if you put A and A complement, they are gonna make the entire space sample,
okay.
right? Okay, so let's continue. Let's talk about mutually exclusive events. What is mutually exclusive event? Mutually exclusive events is events that has nothing to do with each other. Like, let's say this group is flipping a coin, and this group is rolling the dice. What is this event has to do with this event? Is nothing, okay? So we call it like no points of common between the two events. Or event A and event B cannot overlap, but they can be a part of the same sample space. Why? Like maybe I'm gonna make something, like we are in the same sample space and we are gonna flip a coin and in the same time rolling a dice in the same sample space. So all these are outcomes that we are gonna have. So they have nothing to do with each other, but we can include them in one experiment. We're gonna find out a little bit about it. So, all right, let's say that this is my sample space, and this is event A, cannot intersect with event B. Right? So let's say by the way, it can be in the same, like let's say this is A and this is B. The example that I give it to you, rolling the dice and flipping a coin, keep it aside. It still applies to exclusive event, but I'm gonna use it for another example. I'm gonna give you a better example. Flipping a coin. Flipping a coin is gonna give you a head, right? Or a tail. The two cannot intersect together. You either get this or get that. You cannot get one of this or one of this at the same time. So their intersection, they can't be like, they can't have any point of common. You either get head or you either get tail. So let's say head or tail. So the intersection of event A and event B should be 0, right? They shouldn't intersect, or B. They should intersect together. So that's what we call mutually exclusive event. And the probability, by the way, this is the events. You mix two events together. They don't have anything together. But what is the probability that you are getting head and tail at the same time?
0.
Is 0. Like when you flip a coin, you cannot get head and tail at the same time. You either get a head or you either get a tail. 50-50. So the probability of this event, of the probability of phi, is always 0. That's what we call mutually exclusive event. Same thing with rolling a dice. What is the probability of getting 1 and 6 at the same time? You either get 1 or you either get 6. So we call these events are mutually exclusive. Okay. By the way, flipping a coin and rolling a dice is still mutually exclusive. They have nothing to do with each other. The second thing that I want to teach you is called collectively exhaustive events. So what is the collectively exhaustive events? Same thing. I'm gonna make the entire sample. And also I'm gonna focus on the head and the tail. Collectively exhaustive events is still two events, like A and B, that can cover the entire sample. Like, okay, if I'm saying flipping a coin, okay? Event A and event B is collectively exhaustive because they cover the entire sample. Same thing is flipping a coin. All the events from rolling a dice, 1, 2, 3, 6, 4, 5 up to 6, is also collectively exhaustive because they make the entire sample space. It's something like this. Let's say that is event A and that is event B, which is head and tail. This has 0.5 and this has 0.5. Okay? So flipping a coin is a mutually exclusive and collectively exhaustive. The intersection is 0 and the two outcomes make the entire sample. Do you guys get that? All right, I don't want to miss this part. There's something called independent events. So independent events, that's the example that I gave you at first, like flipping a coin and rolling a dice. These are independent events. One event doesn't affect the other event, okay? Same thing, like me giving a lecture here and another professor is giving another lecture in another room. Everyone is a separate event, so events has nothing to do with each other. They don't depend on each other, or me flipping a coin doesn't affect you rolling a dice. The probability here doesn't affect the probability here, because we are going to take in a little bit the conditional probability, two events that they affect each other, but independent effect, they don't affect each other. And the probability of A and B, it is equal to the probability of A multiplied the probability of B. Okay? And these events are something like this. This is A and this is B. That's something like, okay, let's say this group is trying to flip a coin and this group is trying to roll a dice. The probability of getting an outcome here is 0.5 and the probability of getting an outcome here is 1/6. If you want to find the probability of this group to get a hit and the probability of this group to get 6, you multiply the two probabilities together. That is the probability of the two events to happen together. Okay? So that is something like, let's say, flip coin is 1/5, and getting 6 from rolling the dice is 1/6. So the probability is going to be 1/12 of getting ahead and getting like 6 on rolling the dice.
Is this supposed to be union there, or?
This one? No, this is the intersection of two events to happen together. All right. The second thing that we need to talk about is De Morgan's law. What is De Morgan's law? So De Morgan's law is saying, like, consider that you have a bunch of events, event 1, event 2, up to event n. If you find the union of event 1 and the union with event 2, event 3, up to event n, and you try to find the complement of all these, is going to be equal to the complement of event 1 intersection with the complement of event 2, event 3, event n. What this means? This means, like, we are saying neither event 1 or event 2 or event 3 or event n is equal to not event 1, not event 2, not event 3, and not event n. It's the same thing. Okay, this is something like, let's make it simple, like let's say E1, E2. And we are trying to find the complement of these two. So let's put this in a sample space. E1 and E2. What is the complement of E1 union E2? Is the entire sample space except event 1 and event 2, right? So this is E1 union E2 complement. It's gonna be equal to not E1 intersection not E2. If you like in your home, when you go back home, try to make it like a box like this and put just event 1 and another one, just event 2. And if you want to find not event 1, so it's going to be something like this, and not event 2 is going to be something like this. If you try to find the intersection between these two, is going to give you the same thing like this. So this is equal to this plus this. The intersection of that was the intersection of that one. So it's gonna give you all the sample space except E1 and E2. And by the way, this is gonna be in homework 1. You will try to prove the De Morgan's law. Like try to go online and see more about this and try to prove it. So same thing, we can say that E1 intersection of E2 complement equal to E1 the union of E2 complement. All right, so that's a different thing. Let's see how we can do this one. E1 intersection E2 is this part, right? Right? So what is none this part? Everything in the sample space except this part. Right? This is E1 intersection E2 and all that complement. And you are going to do the same thing. Both this one alone and this one alone, and try to find the union of both of them. They are going to give you the same thing. That's the De Morgan's law. Does anybody have any questions so far? We're not going to rely on this rule a lot. Like this is the only time that you are going to see it, but it's better that you know it, and it's better to know how to prove it. Okay. So let's move to the next part. There's something that we need to talk about. It's called the probability, basic axioms of probability, or probability axioms. It's the basics of the probability. So as we said, the probability includes experiment, and the experiment is going to lead to a sample space. And the experiment is going to lead to a sample space, and the sample space has some events, and maybe you are interested in 2 events, A and B, and A and B should belong to the sample space. Like you cannot go to the lab and break some concrete and you said I'm interested in a steel sand. you are interested in the samples that are in your own space. So A and B, that's the axioms of probability. Don't mix things together. So, and you are interested in the probability of event A and the probability of event B. Okay, so the axiom is, so that's the experiment. Okay, that's the experiment. Experiment that you are gonna create some concrete blocks and you're gonna get some sample space, and you are interested in the blocks that are passing the concrete compressive stress. Okay, so the first axiom that we have is, and that's actually intuitive, the probability of A should be more than or equal to 0 and less than or equal 1. And that makes sense. Axiom number 2 is, what is the probability of the sample space? It's 1. What is the probability of all the sample space to happen is 100%, okay? Because the sample space is our 100%, and our events is a piece of the 100%. Okay, so number 3 is, if A and B are mutually exclusive, okay, if A and B are mutually exclusive, what is the probability of A union B?
Root of A plus B.
Probability of A plus B, like let's say that you have these two and they are mutually exclusive, they are not intersection together. Because if they are intersected together, that means that there is something that is repeated in both of them. So you cannot plus them together. Okay? So you can plus them together, but you have to subtract because the thing is, like, they have an intersection. So you have, so the probability of A union B in this case is the probability of A plus the probability of B plus the minus intersection B. Because probability of A and B is always sample space, and the thing is you repeated this twice in A and B, so you have to subtract it one time. But if they are separate, so you can directly say it's the probability of A and the probability of B. And what if they are collectively exhausted? That means the probability of A and B are equal to 1. If they are mutually exclusive and collectively exhausted, which is this, something like flipping a coin. Does anybody have any questions so far? Okay. Is it difficult? I believe all this you guys take at some point, and I mean, long time ago. Like me, it was like in 2008 or 2000, and other people maybe more than that.
1982.
You take statistics?
82.
Did you take statistics at that
Yes,
time?
in basics.
Oh, okay. Yeah, so I believe that's as far as we get in statistics. Like, we're not gonna do more, like, everything is gonna come forward is gonna be about the probability. But we need to understand events, we need to understand like the flipping a coin, we need to understand the intersection, the unions of events. So all this is very important. So let's move to something that is really, really important. It's called the conditional probability. So, and that's actually the basics of the fragility function, because all the fragility functions that we've talked about, it's a conditional probability. It is a probability of having a damage, given that hazard already happened, right? That's a conditional probability. There will be no damage if there is no hazard happen. So conditional probability is the basics for the fragility function. So if you know how to develop fragility functions, you need to focus here. Okay, so let's here. Do you guys remember the independent events that we're talking about? When two events has nothing to do with each other, conditional probability is the complete opposite. That two events has something to do with each other. You need hazard to have damage. Okay, you need something to happen so something else happen. If they are independent, there is no condition. This is not conditioned on this. So conditional probability, we write it that way. We write it as the probability of event A given that event B happens. So we put this in between them. Probability of A given that B already happened. So we can read this as probability of event A given that event B already happened. By the way, which one is the main one? Is B, not A. B need to happen so that you can find the probability of A, okay? All right, so the way to find this is the rule. I'm gonna tell you where this rule came from. The probability of A given event B happens is the probability of A intersection B over the probability of B. That's the rule, and you need to memorize it forever. Okay, let's say that we have an event A and event B. Event A, event B. Who happened first? Event B, right? There's no damage is gonna happen if the hazard didn't happen. So what is the probability of having 20% damage if you got flood depths 2 meters? So which one need to happen first? Is the second event, which is event B. So event B is the one that I need to focus at. All right? So let's say that event B happened. What is the probability of event A to happen? It's just this small piece that happened from A, right? Not the entire event A happened, just this small piece at the intersection. But the thing is, this small piece as a ratio of B, that is the probability that happened. So the probability of the intersection between A and B divided by the probability of the entire event B to happen. So let's say the probability of having flood depths to hit this community, 2 meter flood depths is like 20%. So that is the probability to having flood is 20%. What is the probability that you are gonna have damage? Is this piece over the entire probability of the event to happen, okay? So basically we can read it as the probability of A and B ratio to the probability of the entire event B. So it's the ratio between A intersection B to B. Like this part with respect to the B part. And always make sure that B, like the last one, is the one that is here. Like if I wrote it as probability of B given that A happened, so it's gonna be A intersection B over the probability of A. Right now, what is the probability of B to having given that A already happened? So A is gonna be here. All right, so special case for independent events. So let's say that A and B are independent. What is gonna happen? Probability
A intersection B probability will become PA into PB.
what?
The probability A intersection B will become probability A into probability A.
Probability of A multiplied. So yeah, that's one. So okay, special case. Let's say the let's take this one first. Probability of A given that B already happened is gonna be, let's write actually the basics that we'll learn. I think I have it somewhere Do you guys remember what is the probability of A intersection B for independent event? Do you guys remember when
Yeah.
we flipping a coin and rolling a dice? So we'll multiply the two events together. So it's gonna be the probability of A multiplied by the probability of B. If we substitute this here, so the probability of A, given that B already happened, is gonna be the probability of A multiplied by the probability of B over the probability of B. So you basically slash this with this, and it's gonna give you the probability of B. Or actually, you can make something simple. If A and B are independent, the probability of A conditioned on B is the probability of A, right? Because there is no condition, they are independent. So whatever you are doing here is not affecting me here. So what is the my probability to getting 6 from rolling a dice, given that you get, I don't know, like a tail, it's the same thing. It doesn't affect me. Same thing you can say, the probability of B, given that they already have it, is the probability of B. Something like, you didn't see A. So probability of B given A is the probability of B. Okay, that's the special case that we have. By the way, we can write this in a different way. Like you can, this one can be written as the probability of A intersection B equal to the probability of A given B multiplied by the probability of B. We can write it that way as well. And the same thing, if A and B are independent, so this probability of A given B is gonna be the probability of A, and this is gonna be probability of B, just in case of independent event. Alright? So it's gonna lead to the same concept. Does anybody have any questions so far?
Should I have a question? So, we have a hazard, and then we're gonna like get the risk out of it, which is damage. They are independent events, but they depend based on how we wanna do the relationship between them, right?
No, they are dependent events.
But
You will
why?
never get damaged if you don't have hazard.
So that's the way we depend them on each other.
Yeah.
Because
That's the dependence. Like you will, but when it's gonna be independent, like if, what is, like you are getting an earthquake wave, what is the probability of getting a flood damage? Like if a flood didn't happen, so they are independent. So,
Okay.
but right now we have a hazard that causes a specific level of damage, or a specific damage related to the hazard. So if a flood hazard happened, there's a flood damage that's gonna happen, and they are dependent together.
yeah, so we depend them on each other. We try to have a relationship between
We
them.
don't depend, they are dependent in their nature. Like if there is no flood is gonna happen, we're not gonna get any damage. Let's say not hurricane is gonna hit, nobody's getting anywhere. When you are gonna get, when the hurricane happened. So they are dependent on, in their nature.
Yeah, I understand that, but they are different measurement. That's what's like.
Yeah, but they are still, everyone has its own probability. Everyone has its own probability. Like, let's say, what is the probability if we got hit with 100-year flooding? 100-year flooding, that means it's a 1% chance that you are gonna get flooded. And if you are going to get flooded with 100-year event, I'm going to have a losses of $100,000. Okay, like let's say this is my house, and a flooding event is gonna happen, but it didn't happen yet, but it has a 1% chance to happen, okay? And if it happens, I'm gonna have, let's say, a probability of damage, let's not talk money, let's put everyone has probability. So the hazard has a probability 1% chance, and my house has a probability 50% chance to have damage estate too, moderate damage. Okay, so this one is 0.01 and this one is 50%. If you want to find what is your probability right now to have damage estate to, let's say, the probability of getting flood depths equal to 1 meter is 0.01. 1% chance, because 100-year event is 1/100, okay? And the probability, if you got 1 meter flood depths, the probability of exceeding damage is state 2, which is moderate damage, the probability of you having damage. Let's say when you calculate it, it's 0.5. Like, let's say that you have your fragility function, and it's something like this, and this is 1 meter flood depth, and you get in this function, and you find this as a 0.5, okay? So this is 0.5, and this is 0.01. So what is the probability of you getting damage to state 2, given that flood depths 1 meter happen? That's equal 0.01 multiplied by 0.5, which is gonna give you 0.005. That means right now you have 5 out of 1,000 chance to get damage, which is very, very low probability. Okay? But let's say this hazard already happened, has a 100% chance it's already happened. So this probability is not 1/100, it becomes 100, or sorry, it becomes 1. 100/100 becomes 1. Now you're gonna multiply 1 by 0.5, so you have 50% exceedance probability of damage, state 2. So yes, they are different events, but they are still on the same scale, probability. That's 100%, that's 50%, so they are still having probability.
Okay, I see now what you mean, but in the end, it should be also divided on the probability of the flood depth equal to 1, which is 0.01. Because here it's probability of A times probability of B over probability of B.
That's right, we need to divide over the total, over the probability of this to happen. You need to do that, that's right. But
Isn't
it's
that like,
yeah, you have to apply the same concept. But what I'm saying is, it doesn't, like, if they have different, same thing like when I told you flip a coin and rolling the dice, they're completely different thing. They have different outcomes. But at the end of the day, you are getting a probability from here and a probability from here, and then multiply them together.
okay, I see.
Okay? So having a hazard to happen and the consequences is the damage, yeah, they are completely different things, but they are dependent on each other, and you get probability from here and probability from here, and you multiply them together.
Okay, so we depend them based on the probability, that's the point, like we are trying to do,
Mhm.
like, we are using probability to.
Yeah, we're using, yeah, that's what we're doing,
Yeah,
the probability.
okay.
Yeah. All right, so let's actually do a quick example so that we can figure this out. Example. Okay, let's say that we have an event A, an event B, an event A and B, they make a complete sample space. An event A has numbers 1, 2, 3, 4, and 5. An event B has 4, 5, 6, 7, 8, and 9. And if we put them something like this is event A and this is event B, and they all make up the sample space that has 1, 2, 3, 4, 5, and this has 6, 7, 8, and 9. So they have intersection at 4 and 5. So what I'm looking at, I'm looking for the probability of a given event B happen. What is the probability of event A given that event B happens? So the thing is, we need to find first what is the probability of A, what is the probability of B, and what is the probability of the intersection together. Okay? And actually you can do this with the basics that I taught you, like from first to glance. First, I'm only interested in event B. this is event B. How many numbers that event B out of the total number that it has? It has 6 numbers over 9 numbers, okay? So event B is 6 over 9. So what is the probability of event A to happen? Event A only has 4 and 5 from B, so that's event A to happen has 2 over 5 divided by the probability of the 2 over 9, because that's 2 over 9 from the entire sample, and this is event B is 6 over 9, so it's gonna be 2 over 6. Now let's do it with the same cases. What is the probability of A to happen? I have 9 numbers. Event A has 5 out of the 9, so it's 5 over 9, right? What is the probability of B? B has 6.
6 over 9.
6 over 9. What is the probability of A intersection B? I only have 2 numbers out of the 9, so it's gonna be 2 over 9. So if you wanna find the probability of A given B happen, you are gonna go back to the rule. It's the probability of A intersection B over the probability of B. So this is gonna be probability of A intersection B is 2 over 9. Probability of B is 6 over 9. So this is gonna give you 2 over 6. Same thing. If you wanna find the probability of B given A, you guys tell me what is gonna be the difference. Here is the same, probability of A intersection B. So, what about down here? What probability here is A, which is this one. So always the letter here is the letter here, probability of A. So this is gonna be 2 over 9, and here is gonna be 5 over 9. So it's gonna be 2 over 5. Does anybody have any questions so far? Alright, so I believe that's it for now. Next time we are gonna talk about the total probability theory, so it's gonna get a little bit serious. But you need to absorb all the information that we have here because we're gonna move fast. And I know, I'm not sure if this is too much information for you, but I believe it's kinda like I'm trying to refresh your memory. Maybe you had it from before. So maybe use the weekend to absorb all this information so that we can build on them next time. Maybe you will see, okay, that's like very basics of stuff, but without this basics, you're not gonna understand. And sometimes it gets tricky, you see, like probability and conditional probability and intersection and 2 events dependent on each other and not dependent on each other. So you need like to sit with yourself and keep like doing it yourself. I'm gonna upload the notes on Canvas. I uploaded the recording from the last 2 lectures. I hope that you check them. So I uploaded the recordings from my phone, and also I uploaded the one from the screen. I believe just the first picture, I'm gonna upload the second one and this one today, as soon as I can, and the notes. So try, and I'm gonna upload homework 1. So try to practice homework 1. Some of the homeworks you can use the notes to solve the homework, but some you have to do some research. Like you have to go online and do some research and see how to prove. This has lots of proofs. Like try to prove the Morgan's law. Try to prove that this is equal to this. So you have to do some work on your own so that you can solve the homework. Does anybody have any question? All right. See you guys next time.
When is the homework due?
Next week, I guess, or maybe.